Welcome, data gardeners, to a fresh and vibrant stop in our machine learning journey. I'm excited to be here with you, and today we're diving into a classic classification task using a decision tree. I'm running this in Google Colab, breaking it down into clear code blocks so you can follow along as we cultivate some insights. Let's start by setting up our environment and gathering our tools to explore a beautiful data set about flowers. I begin by loading the essential libraries we'll need for this task. I import NumPy for numerical operations and Pandas for data manipulation, our trusty companions for handling data. Next, I bring in Seaborn to load our dataset and Matplotlib's PyPlot to create a stunning visualization later on. From Sklearn, I import Decision Tree Classifier and Plot Tree for modeling and plotting, plus Train Test Split to split our data, and F1 score and accuracy score to evaluate our model's performance. With our toolkit ready, we're set to dig into the data and start planting the seeds for our decision tree. Now, let's load the dataset. I use Seaborn's load dataset function to grab the iris dataset, and I call dropna to remove any missing values. Though this dataset is pristine, so we keep all 150 rows. I print df that head to take a peek. Sepal length 5.1, sepal width 3.5, petal length 1.4, petal width 0.2, species Setosa. The next row shows sepal length 4.9, petal length 1.4, species Setosa, small, delicate flowers. The iris dataset is a classic in machine learning, featuring 150 flowers across 3 species, Setosa, versicolor, and virginica. Each flower has 4 numeric features: sepal length, sepal width, petal length, and petal width, all in centimeters, plus the species as our target. It's a perfect dataset for classification, capturing the subtle differences between these floral beauties. With the data in hand, I prepare it for modeling. I define X as the 4 numeric features: sepal length, sepal width, petal length, and petal width. These measurements will help us distinguish the species. For Y, I set the target variable as species, Setosa, versicolor, or virginica. Next, I split the data using Train Test Split, allocating 20% for testing and 80% for training, with random state 42 for reproducibility. This gives us X-Train, X-Test, Y-Train, and Y-Test, 120 samples for training, 30 for testing. The iris dataset is balanced, with 50 samples per species, so our split should be nicely representative. We're ready to grow our decision tree. Here's where we plant our tree. I initialize a decision tree classifier from Sklearn, setting max depth to 4 to keep it manageable for visualization, and random state 42 for consistency. I call fit on X-Train and Y-Train to train the model, letting it learn how features like petal length and width separate the species. Once trained, I make predictions on X-Test with the predict method, storing them in YPred. To evaluate, I calculate the F1 score with average set to macro and the accuracy score. The results are impressive. F1 score 1.0, perfect balance of precision and recall across all classes. Accuracy is also 1.0, 30 out of 30 test samples correctly classified. This tree is blooming beautifully, but let's explore its structure to see how it's making these flawless decisions. Now, I dive into the tree structure to understand its decision-making process. I extract key attributes from dt_ classifier tree_. Underscore nodes gives us 13 nodes. Children left and children right define the branches. Feature tells us which column is split, and threshold provides the split values. I set up arrays to parse the tree, node depth to track each node's depth, and isLeaves to mark terminal nodes. Using a stack starting at the root, node 0, depth -1. I loop through the tree, incrementing depths and marking leaves where left and right children are the same. The output shows 13 nodes. Node 0 splits on X column 2, petal length at 2.45, left to node 1 if petal length less than or equal to 2.45, right to node 2 if greater. Node 1 is a leaf, Setosa. Node 2 splits on petal length less than or equal to 4.75, and so on, down to leaves like node 4, versicolor, and node 12, virginica. This structure is a roadmap of how the tree sorts flowers. Let's break down this tree structure further. It's a decision-making garden. The root at node 0 uses petal length less than or equal to 2.45. Setosa's small petals, like 1.4 in our head, go left to node 1, a leaf with all 40 Setosa samples, Gini 0.0. Pure. If petal length is greater, we go to node 2, splitting on petal length less than or equal to 4.75. Left to node 3, versicolor territory. Right to node 6, Virginica. Node 3 uses petal width less than or equal to 1.65. Versicolor's narrower petals, like 1.0. Go left to node 4, a leaf with 36 versicolor samples, Gini 0.0. Wider petals go to node 5, a leaf with 1 Virginica, Gini 0.0, but a tiny misstep. Node 6 splits on petal width less than or equal to 1.75, and deeper splits like petal length less than or equal to 4.95 refined versicolor versus Virginica. With 13 nodes and 7 leaves, this tree is compact and precise. Next, I visualize the tree to bring it to life. I set up a figure with plt.figure, size 16 by 8, and call plot tree with feature names from X columns, class names from dt_ classifier to classes _ Setosa, versicolor, Virginica, filled set to true for color coding, rounded set to true for smooth boxes, and font size 10 for readability. I display it with plt.show. On screen, you're seeing the tree. The root box, orange, shows petal length less than or equal to 2.45, Gini 0.667, samples 120, value 40, 41, 39, class Setosa. Left, a green leaf for Setosa, Gini 0.0, samples 40. Right, a purple box for petal length less than or equal to 4.75, Gini 0.5, samples 80, class versicolor. Deeper, petal width less than or equal to 1.65 splits versicolor, green leaf, 36 samples. From Virginica, purple leaf, 1 sample. The right branch at petal width less than or equal to 1.75 and petal length less than or equal to 4.95 sorts versicolor and Virginica. Colors shift from green to purple as classes change. It's a floral decision map. Let's reflect on these results. They're blooming with insight. The head showed Setosa with petal length 1.4, petal width 0.2, small measurements that fit the tree's leftmost leaf. F1 score 1.0 and accuracy 1.0 mean perfect classification. 30 to 30 test samples, likely 10 Setosa, 10 versicolor, 10 Virginica, all correct. The tree's 13 nodes, rooted on petal length 2.45, nail Setosa instantly. Petal length 1.4 goes straight to node 1. Versicolor and Virginica split at petal length 4.75 and petal width 1.75. Versicolor's petals, around 4.0 length, 1.3 width. Land in node 4, Virginica's larger ones, 5.5 length, 2.0 width. In node 12. Gini 0.0 at leaves means pure classes, no mix-ups. This tree's interpretability gives us that XAI flavor. Small petals, Setosa. Medium, versicolor. Large, Virginica. Clear as a petal. To wrap up this floral adventure, we've cultivated the iris dataset, a bouquet of 150 flowers, and trained a decision tree classifier to a perfect F1 and accuracy of 1.0. The tree's 13 nodes, splitting on petal length and petal width, sorted Setosa, versicolor, and Virginica flawlessly, as seen in our plot's green to purple leaves. This model's clarity, those if petal length less than or equal to 2.45 rules, offers a taste of XAI, showing us exactly how it classifies. Grab this code, tweak the max depth, and watch your own tree blossom. I'm enchanted by this iris exploration. Hope it's got your data senses blooming. See you next time for another nature-inspired dive.